everyone, welcome to my channel Chemistry is Fun. Today we will deal with the topic solutions. This is for class 12. This is for 2025 and it will be continued till 2026. So the students who will appear for exam in 2026 can refer to this video, and this is part 5 of the chapter because earlier parts are already there, so which are meant for 2025 they can also be studied for 2026 board exam. So today we will see vapor pressure of solutions of solids in liquids. First of all, let us see some examples of such solutions. One is solution of sodium chloride in water, or iodine and sulfur dissolved in carbon disulfide. Now we know that liquids at a given temperature vaporize, and under equilibrium conditions the pressure exerted by the vapors of the liquid over the liquid phase is called as vapor pressure. In a pure liquid, the entire surface will be occupied by the molecules of the liquid. That is only natural because it is pure liquid, so the entire surface will be occupied by the molecules of the liquid. But if a non-volatile solute is added to a solvent to get a solution, the vapor pressure of the solution is from the solvent alone because it is a non-volatile solute. Now we know that vapor pressure decreases when we add a non-volatile solute in the solvent because we know that evaporation is a surface phenomena. More the surface, greater the evaporation, more the vapor pressure. When we add a non-volatile solute, the solvent molecules get less surface to escape and has low vapor pressure. And also we know that partial vapor pressure of individual component, whether solute or solvent, is directly proportional to its mole fraction. Now see, in this case, in the solution, the surface has both solvent and solute molecules. So see, when there is a solution, this is pure solvent. But here there is 1 mole of solvent and 1 mole of solute here. So in the solution, the surface has both solvent and solute molecules. So fraction of surface which is covered by solvent molecules get reduced. The fraction of the surface which is covered by the solvent molecules get reduced. And number of solvent molecules escaping from the surface is less, so the vapor pressure is also less. Now just now I told that partial vapor pressure of the individual component, that is solute and solvent, is directly proportional to its mole fraction. But if it is a non-volatile solute, if it is a non-volatile solute, then number of solvent molecules escaping from the surface is less. So the vapor pressure is also less. This is particularly in the case of non-volatile solute. The decrease in vapor pressure of solvent depends on quantity of non-volatile solute which is present in the solution. And we can state Raoult's law. It can be stated as, for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. This only I stated some time back. Here, this is to be noted very clearly that each volatile component, partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. So volatile term is very important here. This only I stated some time back. So important word is volatile here. In a binary solution, solvent is denoted by 1 and solute by 2. If the solute is non-volatile, only solvent molecules are present in vapor phase. P1 is the vapor pressure of the solvent for the solvent, and x1 is the mole fraction. P1 vapor pressure of solvent, x1 is mole fraction. In pure state it is P1 naught. Then P1 is directly proportional to x1. and P1 equal to x1 P1 naught. If we plot a graph, this is between vapor pressure and mole fraction of the solvent, we find that it is linear. It will be like this. Vapor pressure versus mole fraction of solvent. So this is a linear graph we find here. Graph is linear. So I hope students you all could understand this topic which I discussed here today. Thanks for watching my video. Please subscribe to the channel and share the video. Thanks for watching. Thank you.